To understand what's required from a scheduler in a simultaneous multithreading system, let's make some assumptions first. Since we will base our discussion on Fedorov's paper, we will use the same assumptions that she has made, and the figures that we will use to illustrate those assumptions will be reproductions from her paper and her presentation. The first assumption that we will make is that a thread can issue an instruction on every single cycle. So that means that a CPU-bound thread, a thread that just issues instructions that need to run on the CPU, will be able to achieve a maximum metric in terms of instructions per cycle. And that will be instructions per cycle equal 1. Given that we have just one CPU, we cannot have an IPC that is greater than 1. The second assumption that we will make is that a memory access takes 4 cycles. What this means is that a memory-bound thread will experience some idle cycles while it's waiting for the memory access to return. We will also assume that the time it takes to context switch among the different hardware threads is instantaneous, so we won't take any overheads over that into consideration. And also, to start with, for the sake of our discussion, let's assume that we have a SMT with 2 hardware threads. Let's take a look first at what would happen if we chose to co-schedule on the 2 hardware context 2 threads that are both compute-bound, so compute-intensive or CPU-bound. What that means is that both of the threads are ready to issue a CPU instruction on every single cycle. However, given that there is only one CPU pipeline, so one CPU fetch, decode, issue, ALU logic, only one of them can execute at any given point of time. As a result, these 2 threads will interfere with each other. They will be contending for the CPU pipeline resources. And best case, every one of them will basically spend 1 cycle idling while the other thread issues its instruction. As a result, for each of the threads, its performance will degrade by a factor of 2. Furthermore, looking at the entire platform, we will notice that in this particular case, our memory component, the memory controller, they're idle. There's nothing that's scheduled that performs any kinds of memory accesses. Well, that's not good either. Well, another option is to co-schedule 2 memory-bound threads. In this case, we see, however, that we end up with some idle cycles because both of the threads end up issuing a memory operation, and then they need to wait 4 cycles until it returns. Therefore, we have 2 of the cycles that are unused. So the strategy then to co-schedule memory-bound threads leads to wasted CPU cycles. So then our final option is to consider mixing some CPU and memory-intensive threads. And then if we see, we end up with the desired schedule. It's bingo. We end up fully utilizing each processor cycle. And then whenever there is a thread that needs to perform a memory reference, we context switch to that thread in hardware. The thread issues the memory reference, and then we context switch back to the CPU-intensive thread until the memory reference completes. Scheduling a mix of CPU and memory-intensive threads allows us to avoid or at least limit the contention on the processor pipeline, and then also all of the components, both the CPU and the memory, will be well utilized. Note that this still will lead to some level of degradation due to the interference between these 2 threads. For instance, the compute-bound thread can only execute 3 out of every 4 cycles compared to when it ran alone. However, this level of degradation will be minimal given the properties of the particular system.